Hello everybody, today we'll be doing diameter of a binary tree. Given the root of a binary tree, return the length of a diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in the tree. This path may or may not pass through a root. The length of a path between two nodes is represented by the number of edges between them. So here, the maximum difference between, the height, what do you call this? Diameter of binary tree is 4 and 3 because, or 5 and 3 because this is 1, 2, 3, 4, 4 nodes put together. And 3 is the length because this is 1, 2, and 3, or 1, 2, and 3. 1, 2, 3, 1, 2, 3. Why is it 4 and 3? That doesn't make any sense to me. Let's see. So 1, 2, and output the longest difference between, longest diameter between the two is 1. So let's take a look at that. What's going on? So that's one difference. So it's basically the number of leaves minus 1. Okay. Between the two. It looks like what will happen is, what we can think is these are 2 and this is 1, and then we add them up. Now we have 3. Okay, great. That's one way to think about it. So with that, what are some examples about where it does not pass through the root of the binary tree? So let's think about that. So here we definitely pass through the binary tree to get the maximum length. But what if we did this instead, right? Okay, this is a 5. Okay, so this is 6. All right, so what about this? Does this have the longest? Well, what happens here is we have 1, 2, 3, and then that's it. 3 is the longest here because there's nothing on the right side. But, oh, there's also 3 on this side. So, okay, let's try this one more time. Let's move this, shift this forward. And okay, I think we're ready now. So here we go. Let's have some number here. I don't know what it is. Doesn't matter. But this 4, 4, 2, 5, 6 becomes the longest at this particular point because this has a length of 1, 2, 3, 4. And while this has only a length of 3 because this is max 3 on one side, max 3 on the other side, and there's nothing on the right side. So what we learned here from this picture that we can tell is that we have to do this for every single node. So basically, we're going to do a bottom-up recursive approach to go down to the bottom, grab the heights between the two items for each node, and get the maximum diameter. And once we get the maximum diameter for each item, we can go all the way to the top. That means we have to visit every single node. So I'm guessing, so the time and space complexity would be like O of n. O of n for time, because we have to go through everything. And O of, well, it's O of log n for space, because we're just doing this recursively. I think we talked about that last time, about how let's log n, because every time we go through DFS, we go to the bottom, and we throw that information away, and when we get to the next level, so the most amount of information that we need to hold on to is going to the max depth, which is the length of the tree, the height of the tree, which is log of n. Because currently we're doing a diameter of binary tree, and that's log of. So basically, if you have maximum number of nodes, you can only have log n nodes that go all the way down. Okay. So, wait a minute. There is one thing that doesn't make too much sense here. So the thing is, what if our binary tree, right, has a path where it's just completely straight all the way down, like it's like a linked list? Well, wouldn't that be O of n? Well, yeah, that would be if that is true. It could be O of n. So I think either way is the height of the tree. So let's talk about So time is O of n, and space is the height of tree. Okay, with that, we might want to think about one like edge case, which would be like empty, but that's not possible. There has to be at least one node, and with one node, I think the diameter is 0, right? Because diameter of 1 is, yeah. So, okay. So that's what we're expecting. Let's say we have one node, and output should be 0. That's what we're expecting, and we should expect that. So let's try it and make sure that that is the case before we try anything else. So let's run the code. Let's see if it returns 0. Run. It is 0 as expected. Very good. With that, we have done with the edge cases and completed our understanding of this problem, what we're trying to solve for. And we're ready to take the next step, which is to match. The match is, as I said, to do a recursive solution. And plan is to create a max diameter. And we're going to get the max diameter for each node. We will use recursion, depth first search, to find the height between the left and right, and return 1 plus the max of left and right to parent. This way we'll get the max diameter at every single point in our array for each particular node. And I think that's all we need to do. So let's just grab this code and move it down, and let's begin implementation. So first things first, max diameter. We'll set it to 0 because that's the minimum. And let's create our depth first search. So we need some room. Let's make some room and go for it. So definition, the DFS, we'll take the root, we'll take every single node, and we'll pass back an int. So what we're passing back here is not the maximum height difference. What we're passing back here is going to be the height of this particular node. Passes back the height of this particular node. Measure the max diameter per node. Okay, so if not no root, what we're going to do is return 0. Of course, that's our base case. And otherwise, return 1 plus left, max left, and right. So let's get the max left and right. Left is going to be the DFS of left, and right is going to be the DFS of root dot right. Perfect. So let's get that max diameter. So the max diameter is going to be the left plus the right, and the max diameter. Yep, that's it. That's all the code we need. Let's run the DFS on the root node. And what we're going to return? We're going to return the max diameter. Let's run the example pieces of code and make sure that we are getting the answer that we expect. Looks like we forgot the non-local, which we need. Let's take the non-local and get it immediately. Again, this is a method to move the item into our scope. And that is necessary for all pointers that are not by reference. If we use an array, we could be pointing to as a reference, but that would take away the point that this is only a one pointer and we are pulling it from our parent function. So with that, I think we're ready to submit. Let's submit it and see what happens. Oh look, we got a very good answer and we have solved the problem. Okay, so with that, we have reviewed our solution and we are ready to evaluate the solution, and we are is exactly as we said. We're going to do O of n for each node and O of the height of tree, because recursively we only need to keep the height of tree in memory. And that's it. Yeah, it really depends on the height of a tree. The height of a tree could be O of n, so this could just be O of n, given that this is, I mean, we could basically have a linked list. And yeah, if you have any questions, please comment below. If you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much. I'll see you in the next one.